Thank you for that very kind introduction. So the beginning part will be based largely on lecture notes that were developed by Laura Anderson, also who's writing now a book on oriented matroids. So I want to say also, if you find this topic interesting, look out for Professor Anderson's book. So an obvious place to begin is what is an oriented matroid? But I'm not going to start there for a couple reasons. So I want to put this off to later because one is that oriented matroids come in several different equivalent forms. And so answering exactly what is an oriented matroid becomes a little bit complicated because there's a bunch of different answers you can give. And the other thing is those answers don't really make sense unless you have some geometric intuition. And the geometric intuition makes things become much more clear. So a better place to start is looking at what is the role of oriented matroids. And for this, I would describe it as the combinatorics of real linear algebra with sign information, like positive, negative, 0. And why we're interested in that? Well, one reason is real linear algebra is very useful, but the real numbers are uncountable, which makes them harder to work with. You can't record exactly a real number. So something that we want to do with oriented matroids, which will be a theme here, is to try to capture the usefulness of real linear algebra, but with some finite combinatorial objects. So before we get to the definition, the questions we want to look at is first, how do we get oriented matroids from some geometric object? And what do they tell us about these objects? And how are these different forms of oriented matroids related? And I want to motivate, when you start to see these definitions, I want to give some motivation ahead of time for you to think about while you're seeing them. So I want to start with some questions that you're not going to be able to answer unless you already know what I'm going to tell you. So I'm going to define at some point this co-circuit set of a matrix. And this is going to depend on the rows, which I'll denote V1 through Vn of this, the columns. I denote the columns of this matrix V1 through Vn. And from this information, I want you to think, how can you tell if the first column is all 0? How can you tell if the second column is the negative of the first column? And how could you tell whether the first column is a linear combination of the rest of the columns? So that's something you can try to think about when I go through these other definitions. So I start with the sign covector of a matrix. So here, this is, I would just consider here a full rank R by N matrix. And I define the sign covectors as the set of all signs of a vector in the row space of the matrix. So if I give you some example, let's say I start with this matrix. Then I can look at what could I get as from here. Well, I could, of course, take just the signs of anything in any row of the matrix, so I can get plus 0, plus negative 0, 0. Right, and anything that I have in there, I can get a negative of that. So I also have this, and then and so on for the other rows. And the negative of that. And I also have something I could get by combinations, like I could subtract the second row from the first row. So I could get plus minus 0 minus, right? Or I can add all of them together. And many more. So I can think about geometrically what could I get from this? How can I see what this is going to look like? Well, I could draw some picture of these vectors. So let's say I have my first vector v1 going this way and my second going this way, and then v3 will be a combination of those. And then v4 will go the other way. And then v5 will be coming out toward us. And v6 will just stay at the origin. So then I could see, okay, so if I think about what could I get in the row space? Well, I want to take the sign of some matrix. I take some vector in R to the R and I multiply m on the right, and then I take the sign of that. Right? So what I would get is this would still be the same as the sign if I write these as so m here has these columns v1 through vr. This is the same as taking the dot product of x with each of these vi's and then taking the sign of each of those. So a way that I could see that is I could look at the sphere. I'm going to give some of these, and for each of these vectors, I'll draw the orthogonal complement and see how it intersects the sphere. So I have here v1, and then I'm going to draw an arrow pointing in the direction that it's positive. So v1, I think about this as being this great circle on the sphere with the arrow going to the right. And then v2 will be another great circle with this arrow going up, right? And then v3 will go this way. And v4 will just be the same as v1, but going in the opposite direction. And then v5 will somehow cut between all of these. v6 is just 0 everywhere. So you can think here, let me make this a little bit bigger. When I find something in the row space, what I do is I pick out some x on the sphere in one of these cells, and then I see what all the signs are, which I can check by seeing in which direction for each of these arrows is it pointing. So if I look in this first cell here, I would have, well, it's on the positive side of this first circle, and it's on the positive side of the second one and the third one, and it's on the negative side of the fourth one, and 0 for, sorry, it's on the positive side of the fifth one.
You didn't tell which side v5 is.
Ah, yes, I should put that in. Let's make it go this way. So that would give me this. And then I could go across to this cell here, for example. And that would just change the second coordinate from a positive to a negative. And if I go to this point here, this is just positive for the fifth coordinate, but 0 everywhere else. So hopefully this gives some geometric picture of what these things are. I didn't write out all of them, but if we go to the next object, it's easier to write them all out.
What is the name of this V star?
Oh, this is the set of covectors of a matrix.
You always do it on the real field?
Yeah, so in the case of oriented matroids, we're just considering a real matrix. So at least for my purpose. So then we can look at the sign covectors. This is another object we can associate with a matrix. And these are just the elements of V star of minimal support. So I claim that here, since there's not quite so many, I can write out what all of these are. And I already wrote most of them. So actually, so each of the rows of this matrix will in this case be in this set. But there is a little bit more than that. Which is the only other ones I have are these two. Okay, so if we think about
Minimal support. So with the most number of zeros.
most number of zeros, yeah.
I mean, it's not minimal or really minimum?
Excluding 0. So then just non-zero vectors of minimal support. So if we go back to this picture and we see, well, how can you get one of these of minimal support? Well, here these lines that I drew are where one of the coordinates of my sign vector becomes 0. So I want to pick out the places, the cells that are on as many of these as possible. Minimal among inclusion. That was your question. Yeah. Not minimum size of support. Yeah, that's an important distinction. So here I can see this geometric picture. You might consider, well, did I really include all of these? Maybe there could be some more, but from this geometric picture, you can see what they're going to be. They're exactly the vertices of this subdivision of the sphere, right? And I have 4 on one side, and then there will be 4 more on the other, which gives me 8, which I have here. So now I want to put to you the questions that I had brought up in the beginning, which is, how could I tell from this information if one of the columns of my matrix is all 0? Let's say the first column of my matrix is all 0. So I bring back what my matrix was, because this gives some example you might be able to generalize from.
So the last column is all 0 and then covectors 0 or everything?
Yeah, so here I can look, this last column is all 0, and the coordinate is always 0 for each covector in my co-circuit set. Yeah, these are the co-circuits of, yeah.
Oh,
Let me change this.
Co-circuits, okay.
Well,
Covector is the set of all of them.
covectors is the set of all of them.
So that's the V star is for the vectors and the C is for circuit.
Yes, yeah. So there's another one without the star, which we usually go to first, but I like the star one more. Okay, so then the second question is how can you tell if two rows are just the negative of each other?
Or is negative sign. Or
What's that?
first and the fourth one is always negative in the whole circuit.
Yeah, that's good. So then the corresponding entries always have the opposite sign, like in this case, the first and fourth. There aren't that many, but yeah. Okay, and then how can you tell if the first one is a linear combination of the others? So if we think about this question, it would be equivalent, and it may be slightly easier to try to answer the negation of that question. How can you tell that a vector is not a linear combination of the others? Here we have one that's clearly not a linear combination of the others.
One non-zero element circuit.
Yeah, so you have a circuit where just that element is the only non-zero. So you have support just on that. That's good. Okay, so now we can go to another related object. And we can also think about those same questions for this one. So the sign vectors of the matrix, this is the sign of every x where x is in the null space of M. So in this case, if I just bring the same matrix here, I can think, how can I get 0 as a linear combination? Oops. Of these? Well, if I add up the first two, I get the third. So I have a linear dependence like plus, plus, minus. Right? And of course, if I can make it one way, I can always take the negative of that. And then I also have the first and the fourth.
Both plus there, right?
Oh, yes, sorry, both plus. Thanks.
They are both minus for the second one.
Oh, right, yes. And I have
Oh, I see. Yes.
and a bunch of others. And well, maybe to give one more, I have so I could make like a small amount of this one, enough to not cancel that one. So then, in addition to this, we also have the sign covectors. These are, again, the ones of minimal support. So if I take this set, I just cross out this one. So something to consider is how about from, maybe I give first some.
You mean sign circuits? Or?
Oh yeah, these are sign circuits, not. So to get some intuition for what these represent, I will introduce some other notation. So I will write x with some plus, minus, or 0 at the top. to indicate all the coordinates where a certain sign vector is plus or minus, right? So if I write x is, let's just say plus plus 0 minus plus 0, right, then I could write x plus would be 1, 2, 5 in this case. And then x minus, I'll write that as just 4. And x0 will just be 3 and 6. And then alternatively, I can give some sets and then write a sign vector as by writing a plus or a minus above with those sets. So in this picture here, if I'll have a vector among the sign vectors of a matrix if and only if I look at the cones spanned by the sets where they're positive, and the coordinates, the columns corresponding to coordinates that are negative, these intersect. And this is, I think, pretty straightforward to see from the definition. So if I go back to my example that I had before, oh no. Oops. Yeah. So if I go back to the example I had before, I just draw some of them. So I had a V2, V1 going to the right, and V2 going up, and V3 going this way. Then their open cones intersect, which correspond to the vector plus plus minus 0, 0, 0 was one of my vectors in M. So then we can consider the problem of from this information, how could we tell whether one of the vectors is 0? If let's say the first vector is 0, we could look at this. So here again we had a column of all zeros for the last. Yeah. So if you want to see what's that?
If everything is 0 but that one, right?
Yes. Yeah. So if you have a vector with support just at that one position, then that means that column was an all 0 column. All right, and then how can you tell if one is a negative of another? I think you pointed out before you have the plus plus together. And then how can you tell if one is a linear combination of the others?
Minus and
Yeah, there you go. One of them is minus and the others are all plus. Plus or 0. Yeah, that's good.
Do you care about the coefficient? You can say linear combination. When you say linear combination, the coefficients could be negative.
So this is Yeah. Okay. If you're right. So having just a -1 and the other is plus or 0 means it's in the cone. Actually, yeah. So just any vector that has support at that and non-zero coefficients elsewhere. So the last kind of object we have is the chirotope of a matrix. So for this we look at, we pick out some choice of R columns and we look at the sign of the determinant of that, of those columns. So this one I will skip for now because I want to get more to talk more about the vectors and covectors. So one thing is that we saw if we look at the covectors and cocircuits, they give us a kind of cell structure by looking at the orthogonal complements of these, and it's natural to order those cells by containment, and there's a corresponding post-set order on the set 0 plus minus vectors of sign vectors, which is we consider 0 to be less than plus and also less than minus, and then we regard plus and minus to be incomparable. So this gives us a post-set order, which gives us another way of defining the set of cocircuits of a matrix, which is, these are the minimal non-zero elements of the covectors with respect to this order. So one direction of this is quite obvious, but the other direction is not so obvious. So if you have minimal support, then this means that you're minimal with respect to this order. This is just since the only way to go down in the post set is to have more zeros. So, but the other direction, let's say we want to check well, here we could say we could consider something like, can these two vectors both be in right, so maybe it could be the case that we have something, or maybe something like this. Can we have both of these in here? Right. So in this case, maybe this might be minimal without having minimal support. So why we can't have that is we can look at kind of an idea that we can use based on the separating set. So if we have two vectors, we can look at the separating set as the number of positions where they contain both signs. One is positive and one is negative. So we want to consider if we let's say we have some two vectors and suppose the support of y is a subset of the support of x. Right? We want to conclude that x is not minimal with respect to this poset. Well, one possibility, it could be that their separating sets are empty. But in that case, y is strictly less than x, so then x is not minimal. So let's assume, we can assume there is some element and now we can move a little bit, we can look at the ray going from the one corresponding vector to the other. So these sign vectors x and y correspond to some vector in the row space of the matrix that we were given. And the idea that we want to use is we want to find the first z on the ray
Is it null space?
from, no, the null space would be if we looked at vectors, but now we're looking at covectors.
So maybe you have sine x times m and sine y times m.
Oh, pardon?
Because it's a row space.
Oh, so here by W I mean the row space of the matrix, and the covector set is the set of all signs of something in the row space. So this is exactly from the definition. Maybe I go back. Where was the definition? This is just
All right.
yeah. The notation I mean there is the row space, not the rows. Yeah. So we want to find the first z on the ray from x to y that hits some orthogonal complement of some vi. And then we have our sign vectors is this will be less than x. So x is not minimal. And we could explicitly find this by looking for the E in the element in the separating set such that negative x sub E divided by y sub E, the eth coordinate of x divided by the eth coordinate of y is the smallest possible. So that will give us the So another thing that we can see from this, another way of understanding what are covectors is these are, if we look at a hyperplane, we have exactly, the covectors are exactly the partitions where some of the vectors that are positive are on the positive side of a signed hyperplane, and the coordinates where we have a negative are those on the negative side of a signed hyperplane, and the ones that are 0 are exactly on the hyperplane. And then we have it as a circuit. If X is a circuit, if that hyperplane is actually the span of those, the vectors, the columns of the matrix corresponding to the 0 entries. So that you could see from the picture. There's another description of what are the cocircuits, which come from the row-reduced echelon form of a matrix. So for this, we can define a basis as a selection of vectors, columns of some matrix, such that when we look at the submatrix consisting of those columns, the result is invertible, and then we can define the row-reduced echelon form with respect to that basis by multiplying by the inverse of that matrix on the left. And if we think about the usual way of doing finding the reduced row echelon form of a matrix, you would do the same thing, but just you would pick out the greedy basis to get it as far to the left as possible. But we could pick a different set of columns to reduce to the identity matrix. And I claim that the set of cocircuits you get are exactly the sign vectors for some row of a reduced row echelon form of the matrix with respect to some basis. So I think I will not say that much more about that. Maybe I can go back to that later, but I want to go on to a couple other things.
So when you go to the reduced echelon form, you look at the rows there, and
Yeah.
those are the circuits.
Those are the circuits. And then you do that for every possible basis.
Okay.
So it's not, you're not going to get just, if you do pick one basis, then you will only get R of the vectors. But yeah, you have many more. So there's another operation. So another question is, how can we get the covectors from the cocircuits? And this we can get using some operation which is composition, where here we take one sign vector, and if we compose it with another sign vector, we take first the sign corresponding to the first one, unless it's 0, then we look at what the second one is. So if I have like, let's say plus plus minus minus 0 0, and I compose that with plus minus 0 plus minus 0, then I will get this. But this is not commutative, right? So if we go the other way, here we get something different. And
Is it same as making product coordinate ones?
oh, pardon?
Is it same as no? I see. So only when
Because it's not commutative.
okay, right. It's one difference.
Yeah. So something this corresponds to. So if we have the co-circuits of a matrix, we can get the covectors as every sequence of compositions, every possible sequence of compositions of co-circuits in some order. So I'm not going to go through this completely, but I want to point out a little bit about why we get that. So we can think this corresponds to, if we look at x compose y, this is the sign of little x plus some epsilon y for some epsilon small enough.
Positive.
Yeah, epsilon positive small enough. So one thing that we can observe from that is that this is closed under this composition operation. So another thing we can consider is how can we switch between vectors and covectors, and for this we can use hypersum and multiplication for signs. So the way multiplication works is it works just the way you would think for 0, positive or negative. 0 times anything is 0, right? A positive times a positive is positive. Positive times negative is negative. For the hyper addition, 0 doesn't change the addition. If you add two positive numbers, it's positive, or negative, it's negative. But if you add a positive and a negative, you don't know whether you're going to get positive 0 or negative. So we define the output as being the set of all three. And this gives us we can get an induced operation then on sets of signs to sets of signs. And that operation will be commutative and associative. And then we can define, well, we have something analogous to addition. We can define something analogous to an inner product, where we take two sign vectors, we define their inner product to be the hypersum of the product of coordinate-wise product of those vectors. And then we can define two vectors to be orthogonal. And now this gets a little bit weird, because when we take the dot product, we don't get a single value, we get a set of values. So we say x and y are orthogonal as long as 0 is as long as 0 is an element of the dot product. But it could consist of other things. And then we can look at the orthogonal complement of a set of vectors as just the set of everything that's orthogonal to each of the vectors in that family. And from that we can get our vector set from our covector set as just taking the orthogonal complement. So this, it follows similar to what you would do in usual linear algebra. So this was the sign of each vector in the null space of X. Null space of a matrix, right, which is that's the same as the orthogonal complement of the row space. The geometric orthogonal complement. And it works out that this is also the orthogonal complement so this is just an idea, but I'm not going to go through the argument now, which was but then there's a question of how can you relate these two. So, but the last thing I want to get is, I mentioned I was going to give some idea of what the objects are before I get to the definition. But I'm going to get to the definition now of one of the ways of defining oriented matroids, which is these. So these are purely combinatorial objects defined by these 4 axioms. So this is just for either the vector set or the covector set. And they kind of correspond to things that you would think of for vectors, a vector space. So there you have addition and scalar multiplication, and it should be closed under those. So we want to think, can we do a similar kind of thing? Well, so we want to have 0. We can think about this as being the analog of a vector subspace of the set of sign vectors. And so we should have 0 in a subspace. If we have a vector, we can scale it. In that case, if we just have 0 plus minus, the only thing that gets us different by scaling is we get the negative. And then we can think, if we add two vectors, what should we get? Well, if we add two vectors, we don't know what signs we're going to get for the coordinates. But if we make one of the vectors really big and we add just a tiny epsilon to the other vector, then we should get that in our vector space. So it's closed under composition is one of the axioms. And the last axiom you can understand as if you pick two vectors and let's say those two vectors differ in some coordinate, right? They're on opposite sides of some coordinate hyperplane, then you should be able to find some other vector in that hyperplane which is a positive linear combination of those two vectors. And you don't know necessarily what all the signs are going to be, but they have to, in some sense, agree with what you could get as a combination of the two by adding vectors with those signs, and then be 0 on that whatever coordinate it was where they were different. So anything that satisfies these four axioms is the vector set of some oriented matroid and is also the covector set of some oriented matroid. So this is all that I will talk about today.
The hyperproduct, what would be the intuition?
This hypersum.
Hypersum.
Yeah, so you want to think you're adding two vectors and you want to look at all possibilities you could get for signs, not knowing which coordinate is larger or smaller. So let me go back. Yeah, here you can think if you add a positive number to a negative number, it could be positive 0, positive, or negative.
If the two vectors are orthogonal, then either in a coordinate there's either one of them is 0 or they have opposite sign. Is that right? That's equivalent.
Yeah, that would be.
Because then 0 is contained in this hyper.
Yeah, so you could think about you go each coordinate. So if you get a plus somewhere and a minus somewhere, then when you do this addition together, then you'll get a 0 somewhere in that set. Well, there is another issue that, if you just get 0 for some coordinates and plus for other coordinates, then when you add it up, then you'll just get a plus for the total. So it can't be, like if you have like a bunch of pluses and zeros and another with a bunch of pluses and zeros, they're not going to be orthogonal. If there's somewhere where they both agree that they're plus, for example.
Yeah, so either they should be, in a coordinate it should either be 0 there,
Mm-hmm.
there should be a 0 in that coordinate, in one of them,
Yeah,
or they should have opposite. If there's no 0, they should have opposite sign in that coordinate.
yeah.
Is that right?
For each coordinate.
For each
Yes,
coordinate,
yeah,
obviously
yeah,
for each
right,
coordinate.
yeah, for each coordinate, yeah.
Does the existence of this orthogonal covector implies the orthogonal rows in the original matrix?
I'm not sure. So there is one thing I can say is that if you just have something that satisfies the axioms, it might not come from something linear. If it does come from something linear, then I'm not sure. I have to think about that. Thank you for.
Or can you go to the last? I have
Oh,
maybe
yeah.
some more question. This was the last slide?
This is the last slide. Yeah.
So there is some z in that hypersum. Okay.
Yeah. I in subsequent lectures I can explain these axioms more. I just wanted to get to a point where you see see what they look like. I can also point out that there are various different ways of writing the axioms, and this is not,
It's not one I've ever seen before.
yeah, so
So is there a reason for introducing this hypersum? Because I think
it makes some things a lot easier. So this hypersum was actually introduced only in 2016.
Mhm.
But oriented matroids were developed in the 70s.
Yes.
So they weren't, this was not the original set of axioms.
But so I think you've mentioned to me earlier some generalization of oriented hypermatroid. No, I can't remember. So
Oh yeah, so there's,
is that why it's useful to have this?
yes, yes.
notation?
So these,
To use a different multiplication table or something like that? Or?
yeah, so there's a generalization of oriented matroids, which is matroids over a hyperfield, which is satisfies axioms similar to the field axioms, but where addition is multi-valued.
Okay, so it would be easier to go to those if you were
Yes.
used to seeing these axioms.
Yes. It also, I think it makes it easier to see kind of what's going on. More, it's a convenient notation to have for oriented matroids.
I remember that also for the ordered field we can define the oriented matroid. So can it have any some topological understand for this ordered oriented matroid from the ordered field? Something else.
Um,
Real field.
So there are ways that you could put topology on a post set, like think of upper sets as open or something. But in general, I don't know. I'm used to more thinking of just the real numbers or oriented matroids as representing something from the real numbers.
Probably doing linear algebra over some ordered field would give you an oriented matroid, right? Like matrices over some ordered field, not necessarily real. So you
I
still
don't-
probably would get
I don't really think about other fields. I usually just think about the real.
or the rationals would work.
Yes, yeah, sure. Certainly, yeah. Any subfield of the reals, you could pick algebraic real numbers, computable real numbers.
Can you give some overview for what this lecture series will go?
Ah, okay. So that's a good idea. I thought that the time is ended. So isn't it? When is the time until?
You actually can go until 3:45.
Oh, it was I miss. Okay, because there were other things that I was going to do, and I kind of skipped over.
Okay.
So I maybe depending on what you find interesting, but I was going to prove this one, if you like to see that. Although you were maybe interested in seeing where this might go.
Yeah, maybe that would be it.
So, well, so some directions you could ask a question is given something that satisfies these axioms, can you tell whether this is, let's say we're given some V, can you tell, did it come from a matrix, right? This is a question. Or could it have come from a matrix? Is there some matrix and this is one in existential R complete problem, which is the complexity class of deciding if I give you as an input a polynomial, multivariable polynomial, can you decide yes or no, does it have a real root? And so this is, well, one thing you could say is you could just plug in numbers, but there are uncountably many numbers, but you can still write an algorithm that tells you whether it does or not. And this is in p-space. But this is known to be at least as hard as NP hardness. But the exact relationship between those is not known. So this is a reason, kind of a motivation for looking at these axioms, because it's hard to tell whether you have some sign information, whether it could have come from a matrix or not. So we can just say, let's look at the axioms. But then you would say, well, okay, is there some kind of other geometric object that's more general than a matrix or a hyperplane arrangement or vector configuration that this corresponds to? And this would be a pseudo-circle arrangement. So here, if we have some sphere, rather than drawing great circles, we can replace them with something a little bit wiggly like this, and satisfying certain conditions. And as long as, in some sense, as long as these embeddings of a r-2 sphere into a r-1 sphere intersect in a way that topologically looks like how vector subspaces would intersect, then the corresponding object is a oriented matroid, and vice versa, right? Every oriented matroid you can be represented by a pseudo sphere arrangement.
I see. That's surprising. But
Yeah. And then we can also look at something that I'm interested in is looking at the space of configurations. So you can look at the space of all vector configurations, and you can give some topology on this, all spanning configurations. And this is equivalent to the Grassmannian, which is there's some different ways, equivalent ways you can see it. One is as a space of spanning vector configurations, and another is as a space of r-dimensional subspaces of Rn. And you can give that some topology, and then there is a question of how does that relate to oriented matroids. So you can look at all oriented matroids of a certain rank on a certain number of elements and define some poset relationship, which is a weak map, where things become more degenerate if they, things are lower in the poset if they're more degenerate. So I could replace this one pseudo line here with a pseudo line that maybe goes right through this point, and then say this is lower in the poset, which is the weak order. And this defines, from this poset you can define a topology on the set of oriented matroids of a certain rank and a certain number of elements, and then consider if that has the same homotopy type as the original one, as the corresponding space for arrangements of vectors. So those are things that I present later. So maybe I go back to this one. So we could consider how do we know that I give here just some idea of this. So the idea that we want to consider is that a non-zero, if we have a non-zero vector in the row space, this cannot vanish on all elements of a basis. So why is that? So here we pick out, if we pick out some columns that are linearly independent, right? If we do the row reduction, so let's say we find R that's a row reduced echelon form of M with respect to B, then we know that these rows will span the row space, right? So if it were to vanish on all of them, then it would have to be 0. So the intuition is that covectors of minimal support, these vanish on all but one element of a basis, of some basis. But if you pick out some basis beforehand, not knowing what the covector is, it might not be that one. But it could depend on the so each reduced row echelon form matrix, this gives a kind of coordinate system for the row space of our matrix. And so if we write X as some of these coordinates, if it vanishes on all but one, then then we know that actually X has to be just a multiple of that, whichever one it doesn't vanish, right? So this means that the rest of the support of X is completely determined. By B and whichever one it doesn't vanish on. So then we know that X has to be a cocircuit, right? Why is that? Well, how could it not be a cocircuit? The only way it could not be a cocircuit is if there was something else that had a smaller support. So that means it would also have to vanish on every element of the basis except the same one that X vanishes on. The only way you could do that is if it had some extra zeros in some non-basis element coordinate, a coordinate corresponding to a non-basis element. But that can't happen because it's determined by the fact that X has to be a multiple of one of the basis vectors. But then we have to also consider the other direction. So I claim that if X is a co-circuit of M, then if I look at the other vectors that are in the support of, that are not in the support of X, then those vectors have to have rank r minus 1. So for this, if we pick some subset S of the elements, we can define a corresponding space where they vanish so let's say I have some set S. I can look at what are all the X in the row space of M that sorry, I meant to write X. Where the corresponding coordinates in that set, that vector vanishes. Well, if I look at let's look at the set of vectors such that when I apply the matrix M on the right, I get something in this set Vs. Right, so I can write something in the row space as by multiplying by a vector on the left. Then the resulting space that I get will be, I claim, the orthogonal complement of these vectors. So why is that? I have here some vector W, and I'm multiplying on the right by some matrix, and I pick out S, certain columns that are in S, right? And I'm getting 0 at those particular columns, whatever columns that I were getting 0, and it means that the dot product of W, my original W should have been 0 with those particular VIs. And also, M has full rank. So if I look at the dimension of this space, here, if I multiply by M on the right, it's not going to change the dimension of the space. So this will be R minus the rank of VI, R minus the rank of these vectors in this set. So another thing that we can observe is that if you have a subspace of dimension at least 2, then it has to intersect some coordinate plane. Coordinate hyperplane. So at a non-zero, of course, everything intersects at 0. But I mean at a non-zero vector. So you could have like a line that just avoids all of the coordinate hyperplanes except going through 0. But once you have something two-dimensional, if you picked a coordinate hyperplane, it would intersect in a line in general, or it could be contained in the plane. So here, suppose we had that the rank of the vectors that are outside of the support of our x was less than r minus 1, then we would know that the dimension, then we would have that the dimension of the space in our row space where we get 0 in those same coordinates would have to be greater than 1, which means that there would have to exist some y in that space that's non-zero with smaller support. Which means that our original x was not a cocircuit. So I want to go back to what was the issue here. So we have this, we want to show that if we have some cocircuit, some sign vector, which we claim is a cocircuit, if we know that it's a cocircuit, then we can find from that some basis that's going to give us that vector is the sign vector of a row of the reduced echelon form with respect to that basis. This is what we're looking for. So we considered, so we considered such a vector, and we look at things with its support, and we found if we look at the space of things that have that same support or smaller, that support or less, that has to intersect some coordinate hyperplane. So then we found with a non-zero vector, right? Because this is it's going to be a space of dimension at least 2. So that shows that this x was not in fact a circuit. So then we can find, oh, not in. Then we can find our basis. So our claim was that this vi, the set of vectors, the set of columns of the matrix corresponding to the entries of x where x is 0, this has to have rank r minus 1. So then we can choose a maximal independent set I from these and then we can extend that to a basis. So this, however we extend it to a basis, it'll have to be an element that's not in 0. And then x will be either plus or minus whatever vector we get as the row x of the reduced echelon form with respect to that basis. only one of them will have the eth element non-zero. So this is how we can see that these circuits are in fact the rows of some row reduced echelon form of a matrix.